In this video, we're going to actually look at inverting matrices. We're going to give you an algorithm to invert matrices, and then we're going to determine whether or not we actually can invert the matrix. But first, we're going to go through the process of inverting one, see how it turns out. So we're going to talk a little bit about inverting and such. So suppose A and B are square matrices of size n, such that the matrix A multiplied by the matrix B gives me the identity of size n. And also, when I do the multiplication the other way, the matrix B multiplied by the matrix A also gives me the identity matrix of size n. Then we say A is invertible and B is the inverse of A. In this situation, we can say that B is equal to A inverse. Now note, not every single matrix has an inverse, and in fact, matrices, to have an inverse, they must be square and non-singular. But let's go ahead and work through a couple of examples. Now, if we assume that we have a 2 by 2 matrix that is invertible, then we get this first theorem that says I can find the inverse of a 2 by 2 matrix by simply switching the positions of A and B, instead of switching the A11 and the A22, switching those positions, and then changing the signs of the A12 and the A21, which is the C and D here, switching signs, and then dividing by this AD minus BC, which we will learn is the determinant of a 2 by 2, but right now we don't know that, so let's just keep moving. So I am asked to find the inverse of this matrix. I really should check to make sure that when I do this multiplication, I think of this as like a loop type of multiplication like that. I need to make sure that does not equal 0. So A inverse is equal to 1 over, and it is 2 multiplied by 5, and then it's minus negative 3 multiplied by 1, and then my matrix then is going to go 5 in the upper left, 2 in the lower right. This becomes negative 1. This becomes positive 3. So this is equal to 1 over, and then 2 times 5 is 10, plus 3 is 13. 5, negative 1, 3, and 2. And I'm going to go ahead and multiply that 13 through, and so I get 5. 5 over 13, negative 1 over 13, 3 over 13, and 2 over 13. So that is my inverse, and if I were to, which I don't feel like doing, if I were to multiply A multiplied by A inverse, I will find that this does indeed become the identity. If I put A inverse on one side or the other, it will still end up becoming the identity. Boom. All right, so if we are doing the inverse of a non-singular matrix, one of the ways that we can do it is take our matrix and augment on to it on the right hand side the identity matrix. So we take our matrix here, which is negative 2, 5, negative 2, 0, negative 1, negative 2, 0, negative 1, negative 1. We augment onto the identity matrix of the same size. Remember, these should be square. Helps if I can do the identity matrix correctly, 0, 0, 1. And now I'm going to go through the process to make this side, my goal is to make this side the identity matrix of size 3, and then this side will give me my inverse. I'm going to do this by row operations. This will be like the best we've ever done. So what I'm going to do is I'm going to take row 2 here. I'm going to take row 2, I'm going to eliminate this 5 and this negative 1. I use row 2 to eliminate above and below in column 2. So what I'm going to do is I'm going to do 5 multiplied by row 2 plus row 1 back into row 1. Simultaneously, I'm going to take row 2, subtracting off row 3, putting the answer back into row 3. So my matrix now is a negative 2. I'm going to do I'm going to start with the middle row. I'm going to do 0, negative 1, negative 2, my augmentation, 0, 1, 0. And now I'm actually going to do the 5 and the minus. So this becomes a negative 5, and this becomes a negative 10. This is, of course, 0. This is 5. Adding these two together, I'm going to get 2 in the first, negative 2 in the first position. I'm going to get the 0 right there, negative 12 right there, 1 right there, 5 here, and 0 right there. Simultaneously, I'm going to go ahead and subtract off this third row, put it back into the third row. That becomes a plus, that becomes a plus, and that becomes a minus. So adding these, I'm going to get 0, 0, negative 1, 0, 1, and negative 1. So now as I'm starting to produce this into the identity matrix on the left-hand side, I'm going to use the third column, count it third column, to get rid of, I'm actually use the third row to eliminate the values above in the third column. So what I'm going to go ahead and do is I'm going to take, let me see, we'll start out with, let's be wild and crazy and multiply row 3 by a negative 1 and put it back into row 3. Typically I wait to do this to the end, but I'm feeling wild and crazy today, so here we go. Yes, I do breathe on occasion, just not very often. So negative 1 and negative 2, 1, oh wait, 0, 1, 0, 0, 0, 1, 0, and this I'm multiplying by negative 1, that makes that negative 1 and that positive 1. All right, now let's go ahead, now that I have eliminated that negative, I usually wait to the end, but this time I'm feeling wild and crazy, let's go ahead and multiply row 3. So I'm going to take row 3, not 3, row 3 is 2, row 3, I'm going to add that baby to row 2, put that answer back into row 2. Simultaneously, because I'm feeling wild and crazy, I'm going to do 12, row 3. I'm going to add that to row 1, and I'm going to put that baby back into row 1. You were thinking 3, but nope, it's back into row 1. All right, so let's go ahead and do this. I'm going to do the multiplication here. So this is going to be a 2. This is going to be a negative 2. This is going to be a positive 2. So this time I'm going to put my last row, because I am the one that is stabilizing that, and it's going to put those numbers into the other rows with my row operations. And so I'm going to go ahead and add 0 plus 0 is still 0. 0 plus negative 1 is still negative 1. And 2 plus negative 2 is 0. So I'm a 0, negative 1, and 0. Look at that. I'm just so excited. And I'm going to have 0 plus 0, which is still 0 all day long. You're like, yeah, I know. I have negative 2 plus that positive 1 gives me a negative 1. And then I have 2 plus 0 is still just 2. Now let's go ahead and do my multiplications here of 12. So this is going to be 12, that'll be 0, this will be negative 12, and this will be positive 12. Now let's do this addition. 0 plus negative 2 is still negative 2 all day long. I know you were disappointed, think it was going to be something else, but it's not. Moving on. I have 0 plus 0 is still 0. 12 plus negative 12 is 0. Boom, there we go. So 0, 0. We're so excited we just can't contain it. 0 plus 1 is still 1 all day long. And then we have negative 12 plus 5 is negative 7. You had me there. I was almost like, maybe it was something. Nope, it's negative 7. And then positive 12 plus 0 is a positive 12. We are almost there. We are almost to the point of making this the identity. We have 2 steps. We have to divide this entire row by a negative 2. We have to divide this entire row by a negative 1, or in other words, I'm going to take a negative 1/2 row 1, put that baby back into row 1. I'm also simultaneously going to do negative 1 row 2 and put that baby back into row 2, and now I have found my identity matrix, or my inverse. So I have 1, 0, 0, 0, 1, 0, 0, 0, 1. Boom, we have the identity matrix on the left-hand side, which was my big goal for the moment. On the right-hand side, because I divided this by negative 1/2, this will be negative 1/2, this will be 7/2, this will be negative 6. The middle row becomes 0, positive 1, negative 2, and the bottom row did not change from our last set. So there we are. This is A inverse. Cool. There is another way of finding the inverse, and that is using these vectors and these vectors E sub I, and what the E sub I vectors are. These are vectors in which there is a 1 in every position except for the ith position, or excuse me, it is a 0 in every position except for the ith position. So what I mean by that, well, let's actually show you. Let's go through the process of doing this. So we start out with the same matrix. We're going to use the same matrix, which is that A matrix. So we take negative 2, 0, 0, 5, negative 1, negative 1, negative 2, negative 2, and then negative 1. I'm going to augment on my E vector, in which my first position is a 1 and everything else is 0. Now I'm going to RREF this baby like never before. And I get this matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And then my augmentation is negative 1/2, 0, 0. And what this is the first column of my inverse. We call this B sub 1. This is the first column of my inverted matrix. And you notice, bam, we got it right there. We're going to do the exact same thing again, but this time I'm going to, so remember that's our, I'll be crazy. I'll just write it again. So let's just write this again, 1, 0, 0. So let's take this matrix again. So negative 2, 0, 0, 5, negative 1, negative 1. Let's get rid of this piece right there because it's unnecessary. Negative 2, negative 2, negative 1. And now we're going to augment onto a 0 in the second position because we're trying to find the second vector in the columns. So let me just erase this. We already know what that is, so we're just going to go ahead and move that. And when we RREF this, excuse me, sorry, we end up with the identity matrix yet again on the left-hand side. And of course, it helps if I write the identity matrix correctly, 0, 0, 1, and this column, which is 7/2, 1, negative 1, happens to be the second column of my inverse, which is what we have right there. Bam, look at that. Now, let's do our last one. So once again, I start out with the exact same matrix. You're like, wow, this is so exciting. And I said, yes, I know. This is like the best you've ever seen. So we have this matrix one more time. And now we're going to augment on to this vector, in which the 1 is in the bottom position because I want the third one, and I'm going to RREF it. And I expect to get, and I will get, the identity matrix on the left-hand side. And on the right-hand side, I'm going to get my last column, which is, funny enough, negative 6, negative 2, and 1. So notice by doing it in this method, which is a lot of REFing, that this is my first column, this is my second column, and this is my third column in my inverse. Some of the interesting things and kind of important that we get out of this section, the proofs and the theorems are actually in your book. So if you're like, man, I can't sleep, they're there for you. First thing we're going to get is that if the matrix A has an inverse, then the inverse in and of itself is unique to that matrix. If A and B are an invertible, then A, B, invert. I can do the multiplication first, then invert it, or pay attention to the fact that it is now B inverse multiplied by A inverse. They do switch position. It does not become a distributive property. It is not A raised to the negative 1, B raised to the negative 1, A to the inverse, B to the inverse. That is not what happens. It actually switches positions. If A has a matrix and A inverse is invertible, then I can invert the inverse and I get back to where I started, which is kind of nice. Some of the other things that we get is that if A has an inverse and alpha is a non-zero scalar, then if I multiply A by my alpha, which is my scalar, multiply it by matrix A and invert it, it is the same thing as inverting my original matrix and then dividing by, not multiplying by, but dividing by my scalar. If a system of linear equations has a solution of A, X, B, and B, we can solve it by doing the matrix inversion. And you have to pay attention because this is terribly, terribly important, is that if you have AX is equal to B, then you have to multiply the inverse, and it does matter, on the left-hand side of both sides of the equal sign. What I mean by that is notice how my A inverse is on the left and my A inverse is on the left of that as well. So they're asking us to go ahead and solve this. So what we're going to do is we're going to throw this into a matrix, which is 1, 2, and then negative 1, 2, 5, and negative 4. Negative 1, negative 1, negative 4. Then my x vector is x sub 1, x sub 2, x sub 3. And this is going to be equal to my b vector, which is negative 3, negative 4, and 2. Now I know that my x sub 1, x sub 2, and x sub 3 is going to be equal to the inverse of that. And I'm going to cheap and cheese it. I'm going to go ahead and do it on my calculator, and I'm going to get my A inverse becomes 8, -3, and 1 by magic of calculator, -4, 5/3, -2/3, -1, 1/3, and -1/3, and I'm going to multiply that by the vector -3, -4, and 2. And when I do that matrix multiplication, this is what I'm going to get. The vector, when I get all said and done, -10, 3, and -1. So that tells me this is x sub 1, this is x sub 2, and this is x sub 3. Cool. All right, now let's talk about some of the other really cool things we get out of this section and the theorems that we get. Let me move all that up out of the way. Is that if A and B are both square matrices of sign n, then AB is the multiplication of these two matrices is non-singular if and only if each one individually is non-singular. If A and B are square matrices of size n, then if A times B equals the identity, then it doesn't matter the order in terms of the matrix multiplication. They will still become, when I do that matrix multiplication, the identity. If A is a square matrix and A is non-singular, if and only if it's invertible. So this is something that we haven't talked about before. We didn't talk about non-singular being invertible. Now we're saying it is non-singular if and only if it is invertible. If A is non-singular, then there's a unique solution for the linear systems where I have A being the coefficient matrix, B being the constants, and it is A inverse, that inverted matrix A, the coefficient matrix, multiplied by my B vector, which is all the constants. Lastly, we end up with an additional round of non-singular matrices, like I said before. So these all are equivalent. If I say it's non-singular, then it row reduces to the identity matrix. If we say it's non-singular, then the null space of A contains only the 0 vector. If we say it is non-singular, then we know that the linear system has a unique solution for every choice of the B vector. And the next one is the columns of A are linearly independent. And lastly, A is invertible. So I don't know why that's all messed up there, but it should be number 6. So if I say A is invertible, all of this is true. If I say the null space of A contains only the 0 vector, then all of this is true, provided, of course, A is a square matrix. So these now become synonymous with one another. Just a little bit more in this section, so it's not actually 2 sections since we're doing 2 together, is we're just going to remind you the adjoint of A, we do it with an asterisk, is the complex conjugate transposed matrix. We use that information as we define the unity matrix. Suppose U is a square matrix of size n such that U matrix, my adjoint U, multiplied by itself is the identity matrix, and we say U is a unity matrix. Also, what we get from this, by the way, I'm just going to talk about this, and then I'm going to come back to my example here, is we get this, is that if A is only real numbers entries, we say it is real matrix, then the defining property is that it is an orthogonal matrix. And we know that A transposed by multiplied by itself is the identity matrix, then we know that it's an orthogonal matrix. Now let's actually go back to this example right here, and we're trying to show that this is a unity matrix. And so what I'm going to do is I'm going to go ahead and consider my first row. I'm going to call this A sub 1, and I'm going to call my second column, these are columns, A sub 2. Now I'm going to start out with the dot product of these two, A sub 1 and then A sub 2, which is, of course, we know is the inner product. This is going to be equal to 1 over the square root of 2 multiplied by negative 1 minus I, so don't forget the complex conjugate, over 2 plus 1 over the square root of 2, multiplied by 1 minus I, the complex conjugate. And we know when we multiply this together, we end up with 0. And so now we're going to go ahead. So we know that these two are orthogonal. That shows that they are orthogonal. when I do the inner product, or the dot product if you prefer, if they're real numbers, but these are complex, so we call this the inner product. So we've shown that they are orthogonal, the two columns are orthogonal. And now what we're going to do is see whether or not the norm of each column is equal to 1. So I'm going to take the square root of 1 over the square root of 2, the quantity squared, plus 1 over the square root of 2, the quantity squared, and we know that happens to equal 1. So far we have orthogonality, and we have one of the norms, one of the columns is a unit vector. And then we're going to do my other one, so I'm going to do it up here, the norm of the second one, which is going to be the square root of -1 plus I over 2 multiplied by its complex conjugate, so -1 minus I over 2. And then that's going to be added to, again, we're going to take the second entry, which is 1 plus I over 2, and then its complex conjugate, so 1 minus I over 2, and all of this underneath square root, and when I get done, it also equals 1. So we know this is unitary matrix. This is a unitary matrix because, first of all, the columns are orthogonal, and second of all, the norm of each one of these columns is equal 1, so we know this is the unity matrix. Moving on. Here are some important outcomes from the section. A little more important outcomes is if U is a unity matrix of size n, U is non-singular, and the inverse of U is the adjoint. If I have these set of column vectors in a square matrix, so these A1, A2 is the column vectors within the square matrix of A, size n, then A is a unitary matrix if and only if each individual one is orthogonal to itself. So in other words, we have to have an orthogonal set, and they have to be normal, which means they have to be a unit vector. So in other words, they're an orthonormal set. So all the columns are orthogonal to each other, and the columns in themselves have norms that are equal to 1. If U is a unity matrix of size n, and these two vectors come from the complex numbers of size, or vectors of the size n, then what I know is my inner product of my unity matrix by its vector U and its unity matrix multiplied by its vector V is the norm of U and V. And when I do the norm of the unity matrix times the vector V, it's the same thing as just having the norm of V. Why do we care about these? Well, for one of the things, it allows us to view vectors geometrically as directions of forces, and then the norm will equate to the notion of length. So we can start thinking about graphing these and what it does for us in terms of forces. So if you're an engineering student, we're going to actually really start to be able to visualize what's going on with what all of the math is that we set up to get to this point. A couple other things is that we then can find the angle between the two vectors now. So now we've started to set this up. We can find the angle between two vectors. And another reason why we take the time to do all of this is because if you're a computer programmer and you want to make sure that whatever you're programming, especially if you're doing games, is realistic, you need this math to get that character coded so it doesn't jump all over the screen and look weird. You want that character to have a nice smooth movement, and that is this stuff. So that's this video for today. Tomorrow, or the next time I see you, we'll pick up the next one, which is column and row spaces, and possibly even subsets too, because we're going to just wild and crazy it. That's it for tonight.